Chapter 2: The Real Transformer. The ability of iron or steel to carry magnetic flux is much greater than it is in air, and this ability to allow magnetic flux to flow is called permeability. Most transformer cores are constructed from low carbon steels, which can have permeabilities in the order of 1500 compared to just 1 for air. This means that steel cores can carry a magnetic flux 1500 times better than that of air. However, when magnetic flux flows in a transformer steel core, two types of losses occur in that steel. One is termed eddy current losses, and the other is termed hysteresis losses. In fact, real transformers have other losses that occur as well. For instance, copper losses or I squared losses, leakage flux losses, core excitation, and core losses, which we've already mentioned, including eddy current losses and hysteresis losses. Now we're going to go on to look at just how these occur. Transformer eddy current losses are caused by the flow of circulating currents induced into the steel caused by the changing magnetic flux around the core. These circulating currents are generated because the changing magnetic flux sees the core as a single loop of wire. Since the iron core is a good conductor, the eddy currents induced by a solid iron core will be large. Eddy currents do not contribute anything towards the usefulness of a transformer, but instead they oppose the flow of the induced currents by acting like a negative force, generating resistive heating and power losses within the core. Eddy current losses within a transformer core cannot be eliminated completely, but they can be greatly reduced and controlled by reducing the thicknesses of the steel core. Instead of having one big solid iron core as the magnetic core material of the transformer or coil, the magnetic path is split up into many thin pressed steel shapes called laminations. These laminations are insulated from each other by a coat of varnish to increase the effective resistivity of the core, thereby increasing the overall resistance to limit the flow of eddy currents. The result of all this insulation is that the unwanted induced eddy current power loss in a core is greatly reduced, and it is for this reason why magnetic iron circuits of every transformer and other electromagnetic machines are all laminated. Using laminations in transformer construction reduces eddy current losses. Transformer hysteresis losses are caused because of the friction of molecules against the flow of magnetic lines of force required to magnetize the core, which are constantly changing in value and direction, first in one direction, then the other, due to the influence of the sinusoidal supplied voltage or current. This molecular friction causes heat to be developed, which represents an energy loss in the transformer. Excessive heat loss can, over time, shorten the life of the insulating material used in the manufacture of the windings of the structure. Also, transformers are designed to operate at a particular supply frequency. Lowering the frequency of the supply will result in increased hysteresis or higher temperature in the iron core. So, reducing the supply frequency, say from 60 Hz to 50 Hz, will raise the amount of hysteresis present, decreasing the VA capacity of the transformer. But there is also another type of energy loss associated with transformers called copper losses. Transformer copper losses are mainly due to the electrical resistance of the primary and secondary windings. Most transformer coils are made from copper wire, which has resistance. This resistance opposes the magnetizing currents flowing through them. Not only that, when a load is connected to the transformer secondary windings, large electrical currents flow in both the primary and the secondary windings. Electrical energy and power, or I squared R losses, occurs in the form of heat. Generally, copper losses vary with the load current, being almost zero at no load and at a maximum at full load when current flows at a maximum. A transformer's rating can be increased by better design and transformer construction to reduce these copper losses. Transformers with high voltage and current ratings require conductors of large cross-sectional area to help minimize their copper losses. Increasing the rate of heat dissipation through better cooling by forcing air or oil and or by improving the transformer's insulation so it'll withstand higher temperatures can also increase the transformer's rating. The losses that occur in a transformer have to be accounted for in an accurate model of transformer behavior. This model would have to include copper or I squared R losses. Copper losses are the resistive heating losses in the primary and secondary windings of the transformer. They are proportional to the square of the current in the windings. Eddy current losses. Eddy current losses are resistive heating losses in the core of the transformer. They are proportional to the square of the voltage applied to the transformer. Hysteresis losses. Hysteresis losses are associated with the rearrangement of the magnetic domains in the core during each half cycle. They are a complex nonlinear function of the voltage applied to the transformer. Leakage flux. These are fluxes which escape the core and pass through only one of the transformer windings. These escaped fluxes produce a self-inductance in both the primary and secondary coils. In order to make the calculations required of a real transformer, we simply use an ideal transformer with add-ons that, when added to the circuit, produce the equivalent results. This is known as the equivalent circuit of a transformer. Modeling the copper losses or resistive losses in the primary and secondary windings of the core are represented in the equivalent circuit by R1 and R2. Modeling the primary and secondary leakage flux are represented in the equivalent circuit by L1 and L2. The core excitation is modeled by Lm, and the core eddy current and hysteresis losses are modeled by Rc. The bare symbol for a transformer gives no indication of the phase of the voltage across the secondary. The phase of that voltage depends on the direction of the windings around the core. In order to solve this problem, polarity dots are used to show the phase of the primary and secondary signals. The voltages are either in phase or 180 degrees out of phase with respect to the primary voltage. Dots are used to indicate the points in the transformer schematic symbol that have the same instantaneous polarity, points that are in phase. This ends Chapter 2.